Good morning, guys. So I see there are like 17 students arrived already. Let's like wait a little bit of time, like 5 minutes, and start the second lecture. Before we get to the second lecture, I just wanted to ask you guys, how was the lab? Like, did you guys enjoy it? Was it difficult? Was it too easy? The Python programming part, was it easy? The image processing part, did you guys already know how to do these things, or was it something new?
We didn't reach that part about image processing, I believe, but what we had time to do, it was just a good revision.
Okay, so what did you guys do in the lab?
Learn to draw in OpenCV.
Ah, that's nice. Did you guys learn to draw in OpenCV? Was it easy?
Yes, I wouldn't say it was very hard. It was like simple. We learned how to import images, how to take images in grayscale, and to divide the three channels,
Okay,
RGB
good.
and so on. And then after that, we learned how to draw, to create images.
When you when you say draw, like, what do you mean?
How to create an image and then draw, for example, lines, rectangles,
Nice.
circles,
Okay.
ellipses,
Nice.
and so on.
So for example, if I give you like an image and ask you to highlight the area where, for example, a cat is, you're able to do that, right? So for example, put a rectangle on some cat inside an image.
Yes, yeah, we would be able to do it manually, yes.
Ah, that's nice. That's very nice. That's good. So for today's lecture, we're going to like finish basically the first lecture, where we will speak about a little bit about color spaces. And then from there, we will start speaking about image filtering. So again, it's still in the basics of computer vision. The things that we will learn today might be new to you guys, but they will not be difficult, right? So they will be very easy, very basic stuff, something that you can easily understand and basically implement on your own during the lab. And it's definitely something very useful. So even though it's like the basics of computer vision, like these image filtering techniques will stay with you till like if you're going to either an industrial job or more research oriented job. So that's today's course is a bit more interesting, I would say. Okay, somebody's trying to join the wrong meeting. Let me see who this is. Marina Nikolaeva. Marina Nikolaeva, is she here? I think she used the wrong link for this one. Let's By the way, are you like aware if all of your friends are inside? What is it called? Yeah, I cannot even open that meeting. Are inside the Telegram group?
For robotics, all of them there.
Okay, nice. And for computer scientists? For like data scientists, sorry. Who knows Marina Nikolaeva?
She's from the second desk group.
Okay, so can you guys like get in contact with her and like send her the correct link? She is waiting in a different meeting. think there's only like one person in our Telegram group named Marina, so that should be her. Hopefully she read the message. Anyway, since the lecture is recorded, she can follow up later on. Nice. Somebody managed to get a hold of Marina? Well, let's continue. So I hope you guys can see the screen very well. So just like a small reminder on what we have seen on the last lecture, we spoke about like the different types of images. So we saw that there are like grayscale images. We saw that there are RGB images. We've seen that there are different ways to represent each type of these images. So there is something called a, let me see, 1 second. Who else is joining? Is Zoom comfortable for you guys, or maybe we should switch to Teams? I see that there are many people who are trying to join the other.
Well, even Zoom is better than Teams. I guess we should stay.
Yes, for me, it is more comfortable too.
Yes,
I agree also. Zoom is much better than Teams.
Sorry. I think Marina has joined, maybe. Yeah, she's here. Nice. Nice. So let's have like a small revision on what we have seen last time. So we've seen some of the applications of computer vision. We've seen some of the challenges of computer vision, as we've seen. So there are you can take an image of the same object, but from different viewpoints, and they would be completely different objects in terms of like pixels. There are different elimination situations. Some of them are more challenging than the others. There's a huge intra-class variation. And remember this term's intra-class variation. It's very much used throughout the field of computer vision, and especially like when you get to transfer learning and domain adaptation. We've also seen like that objects in motion tend to give us like very bad images, mainly because the images are being taken like vertically. So basically we take this line first, and then this line, and then this line, and then this line. So it's being taken like sequentially. And basically you're taking these pixels before you take these pixels, which makes it like very difficult to work with, what are they called? Moving scenes, right? The second part is background color. So usually when you have like the same color of the background, like the same color of the object shared with the background, it gets very difficult for you to understand what's happening in this image. And yeah, this is a challenge for both human beings and for computer vision models. And occlusion. So basically, as you can see in here, the cow is kind of being hidden by the trees, making it a bit more challenging. We've seen like the human system and the human eye. How does it work? So we said that there's this cornea, this one, and we've seen also the choroid, and the most important part, which is the retina. We said that the retina is basically just a wall that is sensitive to light. So basically when the light travels through this lens from an outside object, it just hits somewhere inside this wall. And since your eyes are kind of sensitive to that light, you get that information traveling to your brain. So basically just like something here sends some electricity to your brain, and for some reason you see images. Yeah, this is a pretty cool thing, and I think you could learn about this from like TikTok or Instagram. It's much better, right? So there's like this, basically there's a place in your eyes where you cannot see anything, right? So it's called the blind spot, and your brain tries to fill in the information of that blind spot, like and pretend like it's actually seeing the whole scene. It's pretty interesting. So after that, we spoke about no need optical illusions, also no need. Yeah. So this is the way that we represent images. I'm sure all of you guys are already familiar with this, but it's important to take a look at it. So here we can see that what we are doing is we're mapping the same way that a human being sees an image in reality. So basically just some values inside a wall, inside your eye. So we're trying to do the same thing with images. So we created a big wall, and basically we have like cells inside this wall in which we can write the values of the different objects, like the different pixels, right? So this is how we represented an image in for laptops. We spoke about the sampling rate. So the sampling rate, for example, in this case, is 265 by 192. So it's basically the dimensionality of the image, or like how good the quality of the image is. So it controls, for example, the clarity of the image, right? So here we have a lot of pixels in the vertical axis and a lot of pixels in the horizontal axis. But here we have like a lower sampling rate, here we have a lower sampling rate, and here we have an even lower sampling rate. So you can think of this like the quality that you get from an iPhone. This is the quality that you get from an older iPhone. This is something that you would get from like, I don't know, Samsung. And this is something that you would get from an older, like super old phone. Now, the second thing that can influence the quality of the image is the quantization, right? So basically how many bits are used to represent every pixel. So in this case, we have like the clearest image with 8 bits. So 8 bits means like you go from 0 to 255, right? Here we have something that is represented on 6 bits. Here we have something that is represented on 4, and here we have something that is represented on 2 bits. 2 bits mean you can only represent 4 colors. So you can see that this whole sky thing is represented in 1 color. For example, here you could see that there was a cloud in this area, but in this image you can no longer see the cloud, right? So it's same thing. So this is like one of the problems that you get with quantization. Like the less bits you are using, the more difficult it is to understand what's happening in the image. But at the same time, this image takes a lot less size, and hence it does require a simpler model to work with, right? So it's kind of a trade-off. This requires a very difficult model. This one requires a more simpler model. Yeah, we spoke about the sampling rate, but it's not very much a problem of computer vision. This is more of a problem of photographers. Image representation. So we said you can have like different grayscale images, RGB images, depth images, medical images, which could be like 3D or 2D, and we have the heat images, right? So we said that black and white images, something similar to this one, require only basically 1 bit. 1 is for white, 0 goes for black. Gray scale images or gray images, they take a representation from black towards white, where white is 255, and everything in between takes a number from 0 to 225. We've seen that like colored images are, as you can see here, they're definitely more useful. So you can easily spot this rabbit in this case, mainly because the grayscale of this of the grass is very similar to the grayscale of this object in here, making it much easier, like making it much harder to basically distinguish the two of them. But when it comes to colored images, the difference is definitely more visible. But how do we basically represent these colored images? So one way, of course, is RGB, which we're already familiar with. But another way, which could be more interesting, is based on this theorem, right? So here we have the Sir Isaac Newton's theorem. And what he said is that you take some light, source of light, white light, and you send it through like a glass or some sort of water. And basically the output is this rainbow, these rainbow colors. And well, something very interesting about these rainbow colors is that they are kind of ordered, right? So you can see that they are ordered, meaning you could easily put a scale from 0 to, for example, 255 that kind of represents all of these colors, right? So this is just one interesting way of representing colors in one value, right? So here you can say, for example, this based on the wavelength. So here you can say 400 means that you are speaking with violet, purple, I think that's the name in English. And 510, for example, goes to green. Orange is 600, let's say, and 700 is for pure red, right? So this is one way to represent the content of an image, right? Nice. Yeah, so this is just a small, I think you all had this in high school. So when you combine, no, no, this is not what you had in high school. Yeah, let's go back to what you had in high school. When you combine, for example, green, for example, blue and red, what do you guys get?
Purple.
Nice. We have a high schooler here. And when you combine, what is it called? Green, not green, no, the other color. I forgot
Yellow.
the name. Yes, yellow and blue. What do you guys get?
Green.
And when you combine red and yellow?
Brown. Red and yellow, orange.
Nice, very nice, good. So yeah, for us, we are not using red, blue, and yellow. We're using red, blue, and green for some reason, right? Apparently, it's much usefuler, much easier to use this representation. But for us, here we have like something, the secondary colors that can be created from these primary colors. They're kind of similar idea to what we have discussed right now, but these are a bit different, right? So here, for example, when we combine green and blue, we get this cyan color. Do you guys know what is cyan color? Have you guys seen it before? Yeah, so it should be somewhere like this, right? Somewhere around here. When we combine, yeah, there is. Yes, here it is. So this is the cyan. When we combine red and green, for some reason we get yellow. This was a bit weird for me, but why not? And when you combine blue and red, you get this magenta, right? So one very interesting feature about these colors is that when you sum them up, you get the white color. And there is this subtractive primary colors property, right? So basically what it says, when you combine all of these, for example, I think this is better explained with, what are they called? The things that you guys draw with, right? So if we use the colors that we are drawing with, and we combine all of the different colors that we have, we get black. And if we use light and we combine different colors of the light, we get basically their combination becomes white. Something very similar here. So when we subtract basically this CMU, which is like white, cyan, magenta, and the yellow, we could get the black color. So basically, yeah, it's a bit weird for me, again, saying this concept is a bit weird for me because I'm not very good with light, and physics, both of them. But basically, this is very useful for us when we are going to do some filtering a bit later on. The color spaces that we might already know. So RGB, this is like the most commonly used. There is a cyan, magenta, and yellow. This is also very much used in printing. We have these others, and you should not worry about all of these others. But I think HSV, HLS, and HSI are quite useful. So hue, saturation, value, hue, luminance, and saturation, and hue, saturation, and intensity. So you can see that between all of these two, between all of the three, hue, saturation is always in common, and then another third value is used in combination. So this one is close to the human's interpretation of color. So let's take a look at it and see how it's working, right? So first thing we should look at is basically, this is a colored image. This is what it actually looks like. This is what you guys see. And this is how it is being represented in different channels for example, this cyan, magenta, yellow, and K, or black components. So for example, in the yellow part, you cannot use this channel to understand if there are fruits in this place. Same thing for the magenta part, it's quite difficult. But for the cyan and the black images or channels, you can easily spot the shape of the fruits, right? So this tells you that different channels can be useful for different processings down the road, right? RGB in this case, so you can see that the blue still not very clear. Same thing for the green channel and same thing for the red channel. So none of them actually is, well, very useful for the detection of these what are they called, fruits. Whereas, for example, this HSI, intensity HSI components, so we can kind of see that this one is kind of good. This one, not very much useful for the detection of the objects. This one is a bit more useful, but still it's not perfect, right? So here we have like our way of representing a pixel in RGB. So basically we have a pixel is just 3 values between 0 and let's say 1 or between 0 to 155, right? So here we have grayscale points, which go from black to white. So it's a line that goes directly between black and white. And in this case, you can see that, for example, if we speak about 0.5, 0.5, 0.5, that is gray value. If we say 0, 0, 0, that is also considered kind of like black, but it's like in the grayscale values, and white, which is 1, 1, 1, 1. So basically, when we have the same values for green, the same value for blue, blue, and the same value for red, the RGB representation will be a grayscale value. So for example, for those who are trying, for example, to convert an image from RGB to grayscale, your job is to basically find the point in its grayscale line that kind of maps it or keeps as much information as possible. So yeah, the color depth is basically 224 bits, meaning we have 8 bits for the this channel, 8 bits for the green channel, and 8 bits for the blue channel. And basically this is how they look like. We combine all of these channels into one colored image. Now let's speak about the this HSI color scale or color model. It's kind of pretty interesting or pretty important for many of the computer vision systems, since it's quite heavily used for processing. So what it says is that RGB is very useful for hardware implementations and luckily related to the way in which the human visual system works. However, RGB is not particularly intuitive, does not use a particularly intuitive way in which it describes color. Rather, when people describe color, they tend to use concepts such as hue, saturation, and brightness. So let's go and understand what are these hue, saturation, and Sorry. Yes. So what is, so let's take a look at what hue, saturation, brightness are, right? So here for the HSI model, we have the hue, which is the dominant color. We have the saturation, which is a measure of how much a pure color is dilated with the white light. So these two represent the color information. And we have the intensity, which is the brightness, right? So all of these values can be extracted from RGB, and I hope that you guys have already done this in the lab. So I will try to go a little bit easier on this one. And yes, so for example, remember this diagonal line that goes for RGB color cube. It goes from black to white, and it represents our grayscale images, right? So here we have our formulas that can map basically hue or RGBs to hue, saturation, and intensity. So for the intensity or the brightness, basically what we are doing is taking the average of all of them. Here we have the saturation, which is a measure of how much a pure color is diluted or something with white light. Yeah, basically what they're saying is it's 1 minus 3 divided by their sum multiplied by the smallest of the 3 channels, right? So here, for example, if all of them are very close to white, then basically you will have 1, or let's say, yes, 1 multiplied by 3 divided by 3. So 1 minus 1 is 0. If they are all black, for example, so it's basically 0. 3 multiplied by 0 divided by, let's say something that's not 0. So 1 minus 0, it's 1, right? So this is basically how this is working. It's just it's a measure of how close you are to the white point. Now this thing here, I have no idea what it's doing, right? So it's a very complicated formula, and honestly, it's horrible, right? So, but it definitely kind of represents the color in a certain way. So basically, it puts both RGBs or puts all of the RGB values in a sort of like a line that allows you to represent all of these images, all of these colors, in the same manner that we have seen on the rainbow thingy. Now, if you would like to convert back from HSI to RGB, I would not say it's simple, but it's kind of ugly, right? So here are like the different kinds of mappings, right? So mainly it's due, I think, to, sorry, every time I touch it, it just goes away. So these are like the 3 different sets of formulas that you can use depending on the value of H. So if you can see, as you can see here, H does have different values for different conditions, and mapping it back does kind of require also a couple of conditions. But it's, again, very simple, something that you can easily program in NumPy in like a couple of minutes, right? Yeah, so here we are like doing the calculation of it, but very important application is the following. I hope you guys have done this in the lab yet or not yet.
Not yet.
Okay, from what I've spoken with Karam, he told me you guys already did this part. Maybe some of you guys did this already or not yet?
Yeah, some of us already did this, but some of us
Did not.
Not yet. Yes.
Okay, so good. So it's just a small color application, which is for skin detection. Yeah, basically what they said is they created this kind of, what is it called? Condition that can allow you to detect where is the skin part of an image, yes, automatically, right? So of course, these values, for example, 0.2, if the saturation is higher than 0.2 and the luminance is between 0.5, luminance divided by saturation is smaller than 28, or hue is bigger than 330 degrees. So this is what it's saying, but basically what it is, it's a condition that was created by a human being. So basically a human being was just trying to change all of these values and try to find something that can easily detect skin. So as you can see, it works kind of well for the skin. So it does detect where the skin part of the image is, but it doesn't work very well. So for example, it is detecting that this is skin, 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 and all of these are skin. So of course, one person might say that we could process this image a bit further or process this result a bit further and clean it up. Basically, let's say if we know that skin is something that is very continuous, right? So if you find objects like this with big holes inside, something like this with a big hole inside, or something like this, so we can easily just like make some other if statements that can clean them up, right? Or make an algorithm that basically like looks at the neighborhood of a place. If all of the neighborhood is activated, this is a skin. If most of the neighborhood is deactivated, then we consider this not a skin and basically remove all of this extra noise. But this is for the next lecture. For now, this is like another application, which is red eye detection. So basically they're trying to detect this red eye part of an image. You can see the algorithm kind of works, but it doesn't work very well because it detected this part, this part, this part, this part, this part, and of course the red eye part. So basically what this is not like a red eye detector, but this is a red detector, right? So basically it's detecting anything that is remotely red. But still, this is something that you get for just one single if statement, right? So it's pretty easy to, well, it's pretty cheap to get. So, well, this is it for the first lecture. I hope that by tomorrow, all the groups would be in the same range. So, or advancement of this, of the lab. So I'll speak with your teaching assistant, and we will try to basically get all of you guys in the same speed. Just to confirm, which group has already done this part and which group has not?
I think it's not about groups, it's like about particular people who just went a bit further during the lab.
Ah, okay. So, so the lab goes basically. He gives you the lab, and you guys go through it on your own pace, right?
No, like he explains a lot, but some people already know stuff. They just go further on their own.
Ah, okay. Good.
Yeah.
Thanks a lot. Thanks a lot, Anna. Thank you. Nice.
I think officially nobody has done it, I guess.
Okay, so this is nice. Okay, this is nice. So basically, next lab, you guys should finish this part together. Okay, that's okay. Yeah, that's much better. So let me try to fix this presentation a little bit. Ooh. Yeah, this is why I hate Windows. Anyway, so basically now we will get to the next lecture. The next lecture is pretty easy, and it's about image filtering techniques, right? So remember when we have seen that the output of the skin detector, it was very noisy, it had a lot of problems. So now we're going to check some techniques that can help us to reduce this noise in general cases, right? So for that specific case, we could apply different, more advanced algorithms. As I said, based on like some heuristics, saying, for example, the skin is a very continuous object, so it should not have a lot of like holes inside of it. This algorithm or this heuristic can be implemented and it would give you much better results. But for now, we are going to take a look at some of the easier or more generic image processing techniques, right? Just so you guys know, this is from, this is inspired basically from Professor Ali Khan's course. This is also based on the Practical Introduction to Computer Vision course, and some found on the internet. And definitely this is completely inspired from Professor Fahim's course. So if you guys see that the first half of the course is a bit too easy, I'm sorry, I really cannot make many changes to this part. So since, well, according to what we have discussed with the education department, they really want you guys to focus on these basics. So we are going to try and give you exactly as much of these basics as possible. Whereas on the second half, I will go ahead and make it as much advanced as you guys want, right? So depending on the results of the poll that I gave you, I will try to give more attention to different types of topics, okay? So small recap. So again, we can think of an image as a function, right? So a function of x, y, such where x and y are just coordinates of the pixel, which gives you the intensity at a position x, y, right? So we can think of a colored image as just like three functions where we can write these as a vector value function. So here f of xy equals a vector of r of xy, green of xy, and blue of xy, right? So we can still think of an RGB image as just a picture that gives you, instead of just one value of intensity, it gives you like three values of intensity. When I say intensity in this case, I do not speak about HSI. What I'm speaking about is basically the pixel value, right? So imagine that we are still speaking about the retina wall, and we represent an image by, or we represent the color or pixel by how much activation it is sending to the brain, right? So basically this is kind of like the way that you guys should be thinking about the intensity, right? So image processing phase should help for three main tasks, basically facilitating the extraction of information, or compensating for non-uniform illumination, and readjusting the image to compensate for distortions. So again, the main part that I would say that image processing is usually used for, first one is explaining or facilitating this extraction of information, cleaning up after the extraction of information, or introducing noise and improvements to the model. There are three main classes of operations that we can see in image processing techniques. So there are the point-based, like point operations, there are the neighborhood operations, and there are the geometric operations. Well, point operations are pretty much the simplest kind of operations that you can have. So basically it deals with pixel intensity values individually. So I take this value and I look only at this value to map its corresponding value on the other side, right? So the intensity values are altered using particular transformation techniques as per the requirement. Example, we have a background subtraction algorithms, we have thresholding, we have contrast enhancement, and we have brightness enhancement. So somebody, yeah, I think you still haven't done this yet. But for example, if we used our algorithm of before for the skin detection part, basically what it should give you is just like a set of pixels, right? But if you, in reality, you used this, let's say, skin detection algorithm, but found something a bit better. Let's say you found a grass detection algorithm. So what you could do is you could detect all of the grass around, let's say, an animal, and using a point-based operation, you could subtract all of the, what is it called? All of that background you detected, and basically you will have a PNG image, right? So basically with a transparent background, right? So these point operations, you can find them already implemented in many of the software that you would use for image processing, such as like Photoshop and stuff like that, right? So they're very famous there. Yeah. So for example, here we have, this is a current frame. This is our background model, and we're trying to find the foreground mask, or we're trying to find an object that is moving, right? So pixel values of two images are subtracted on a point-by-point basis. So we take this point, we subtract it from this point, they are the same, meaning this point did not change. We take this point, subtract from this point, also black did not change. We take this point, subtract it from this point, there is some change, meaning there was something that moved or something that was introduced in this area, right? So it's based on this notion that motion detection, for example, stationary objects cancel each other out while moving objects are highlighted, right? So if you take, for example, frame number 50, and this is frame number 0, you can easily find out what are the objects that are new inside the image, right? So for somebody who's trying to build some sort of a security detection, right? You have like a camera, or you have a video stream coming forward. You take the first image and then basically keep on doing the point-by-point subtraction. If you find a shape that is suspicious, that means that definitely somebody is trying to steal whatever you are trying to protect, right? So it's easier to do an object detection on this mask than it is to do it on this kind of image, right? So even if you are not familiar with bigger models for object detection, or for example, for some constraint, for some reasons, or like industrial constraints, you cannot use a model as big as like YOLO or as big as RCNN. So you could easily just use a simple model that looks at this foreground mask. This foreground mask is, honestly, I think it's like 200, let's say 280 by 280 pixels. So it's not like big, and each pixel is represented only on 1 bit. So it's a very small image. You can easily send this forward to what is it called? A linear regression, or to a simple decision tree, and build your motion detector. Another very cool example of this point operations is contrast enhancement. So a very simple one would be to multiply all the values by 2, right? So remember, a black is 0, white is 1. So if we're trying to basically see the values or see the image a bit more, what we could do is multiply everything by 2, and we would get to see an image that is a bit brighter, right? So this is one algorithm for contrast enhancement. The second algorithm, which is a bit more advanced. So it's, yeah, here's the results. So remember this with, sorry. So this with this, this with this, which one is better? The original image is the same. For the output, which one is clearer for you guys?
Second one.
The second one, very nice. So the second one is pretty simple idea. What they're saying is small, or yeah, black-ish values should get blacker, and white-ish values should get whiter. Let's do it a bit cleaner, like this, right? So they're trying to make the blacker points blacker and the whiter points whiter, in order to basically make more contrast between these images, right? So what's happening here? Okay, let's not look at the formula right now. Let's look at the shape of this formula first, and then we will look at the formula and understand it a bit better. So what's happening is this is the formula based on different hyperparameters, right? But the objective is always the same. What we are trying to do is we are trying to make blacker points. So for example, 0.4 in this case becomes 0.2 or 0.15, right? So we're trying to make something that is already black, we're making it more black, and something that is already white, let's say for example 0.7 here, we are making it 0.9. So we're making it a lot whiter, right? So this enhances kind of the contrast between like the different borders and gives you these borders that can be easily detected now, right? So for example, if you give some edge detector algorithm this image, it might have some difficulties to find all of these different edges, but in this case, it's going to do it very easily. So this is contrast enhancement technique is definitely more useful for such applications. Now, what's happening is basically we are determining the concept of what is black and what is white by a simple threshold. So we put this let's call it, yes. So we put our points. So this is pixel 1, pixel 2, pixel 3. These are the different pixels that we have. We take the mean or the average of these pixels and put it here. Anything higher is considered white or white-ish pixel. Anything lower is considered black-ish pixel. And we try to push them a bit further away, right? So anything on this side goes here, anything from this side goes even further. And here is the formula to do that. So S, well, basically it's the contrast stretched pixel equals 1 over 1 plus M. M is the mean, R is the original image to the exponent of E. So E is your hyperparameter, and as you can see, it controls how much contrasting are you doing. So the higher the E, the higher the contrasting is happening, right? So just to see, for example, how is this happening here? So let's like replace these values with something that we can work with. So let's say it is 1 plus, here we have 0.5 is the threshold, divided by R. Let's say R is something that is already too white, so 0.7 to the power of 5. Can somebody tell me what is this value? Somebody do the calculations. Or let's do it on Google from the side. So 0.5 divided by 0.7. To the power of 5. Okay, 1 divided by this. Yes. So this gives us 1.1, and 1 divided by 1.1 gives us 0.85, right? So we started with a 0.7, we ended up with a 0.8. Now let's try and do it for something that is small. So 1 plus 0.5 divided by 0.2 or 3, right? To the power of, let's say 5. Let's do it together here. 13. Really? Yeah, could be the case. So 0.5 times 3. Yes, so it's higher than 1, so it becomes, yeah, very small. Makes sense. 1 divided by this. Oh, sorry. Gives you 0.07, right? So we started with 0.3, we went even darker. And this is the point of this algorithm, right? So what it's trying to do. Yes, of course, go ahead.
Yeah, sorry for interrupting. In which cases would it make sense to shift M, like to make it 0.6 or 0.
M.
Yeah, M.
M is always shifted, right? So M is something dependent on the image. So for me, I used M as 0.5 because I was using a hypothetical image. But for some reason, for example, in this case, all of our pixels are, for example, this is, let's say, 0.5, and this is 0.2. All of our pixels are between 0.2 and 0.5. Makes no sense to put M as 0.5, right? It would be useless. It would do nothing to your image, right? It would make it just a bit worse. So M is very dependent on your image. Basically what M is, so it's the middle line or the mean of all the pixels. What you do to calculate a good value of M, it's basically to take all of the values of these pixels and take their mean. This is just a basic understanding of what M is. But if you can find a better M, meaning, for example, you already know that your foreground objects, which are these, for example, they have like pixel intensities of 0.8. And you know that there is a lot of background, meaning if you take M as mean, it will be highly influenced by the values of the background. So you know that the background is usually in 0. Let's say 5. You could set a value for M manually based on something that you already know. So if you are working in a specific field, for example, you are working in the field of what are they called? Those things where you have like you take blood cells and you put them through the micro thingy. What is it called? The thing that allows you
Microbiology or something like this.
Yeah, that microbiology stuff, right? So it gives you just pictures like this, right? So of the cells inside the, like, this is the picture, right? You guys have already seen these kinds of pictures, right? So this is what they do for medical images analysis. If you are working in a specific field and you already know what should be the optimal value of M, then you could go ahead and use that. Very well. So that's it from the point operations. Now let's go to a set of different type of operations, such as the neighborhood operations, right? So the neighborhood operations, for example, we have in here. What we are trying to do is, based on what's surrounding the pixel at the original image, we will create the new pixel at the other side here, for example, right? At the output pixel. So here, for example, the size of this neighborhood that we are looking like can vary a lot. So yeah, so for example, here you have 3 by 3, 5 by 5, or 63 by 63. For those who have already seen convolutional neural networks, the convolutional operation was like invented before, of course, CNNs, but it was not used as a operation for like neural networks and detecting objects and stuff, but it was used as a neighborhood operation to pre-process images, right? So using this window size, we can change the set of pixels around here and get a new pixel as output. Sorry.
So we like take, could I ask about the previous slide? So we can take a mean or something.
Very well,
again.
very well. Yes,
Okay.
exactly. You can take anything you guys want, right? So we
And
will define this. Yeah, we will define what are the different types of these neighborhood operations like very soon. Yeah. They could be used to apply some logical tests. So basically, for example, in neural networks, they are used to apply some tests to detect the presence or the absence of some sort of object, right? So we use this convolutional operation, for example, to detect noses, right? To detect the mouth of a human being, to detect all of these concepts. We are trying to either activate when we find them or send 0 if we don't find them, right? So this is the point of these neighborhood operations. They could be used for this application. What they're mainly used for, or simply used for, object removal of noise, object thickening or thinning, and erosion and dilation. So contracting and expanding an object. What does it mean to erode and dilate? So basically, let's say we have an object like this. Let's say, so we have this cycle like this, right? But for some reason, we have a dent in here. So this is not like, yeah, I cannot do it. Let me close, let's do it slower, right? Slowly. Nice. So you see, let's say that we already know that this should be a perfect cycle, but it's not. So we could apply some operations that would allow us to connect basically these two dots and fill in all of these values, right? So these are like the applications where this can happen, where this is useful. So it's basically, remember when we had the skin detection, right? So using this application, the skin that we have created like this, and it had some noise here. So some of these points were taken out. So we could use a technique that basically reconstructs all of this area clearly, right? So this is just basically one of the application areas of these neighborhood operations. So let's say, for example, the convolutional operation of an image F with a kernel or a filter or a mask. So depending on the situation where you are working with. So for example, in neural networks, we use the word kernel and filter. Mask, we also use it in preprocessing. So let's call this H, right? So this is the convolutional operation. The function H is normally referred to as the filter. So what it does is it dictates what elements of the input image are allowed to pass and what elements are not allowed to pass by choosing an appropriate filter. So choosing an appropriate filter, either using manually, so human beings look at it and try to build this filter for specific cases, or by training it using a neural network, we can enhance certain aspects of the output and attenuate others. So just like a small side point, remember when they said that convolutional neural networks take away the image pre-processing part from human being, or the image engineering part from human beings, and give it to the machine's responsibility, right? In fact, what was happening before, like CNNs, was that well, engineers used to like stick together and like have lots of meetings for like long periods of time, and they tried to find the weights of these convolutional filters manually for specific cases. So for example, for face detection, for facial, for face detection and to detect the face of human beings, and for like car detection and stuff like this, they used to create these convolutional operation and these kernel weights manually, right? Now with neural networks, this part or this pre-processing part is automated for us. So you could build or detect all these weights using neural networks without having to do it on your own. Nice. So this is just how you guys would do the operation of, what is it called? Convolution. I think you guys are already familiar with convolutions. So it's a very simple operation. Do you guys already familiar with convolutions or not yet? I'm assuming Professor Khan already did this, right?
Yes.
Yeah, so how many lectures did you guys have with convolutional neural networks?
One,
Just one?
maybe two, but not so many.
Ah, okay, so you're not very familiar. Oh, okay, sorry. Usually I teach these courses for like those master students who are like have spent like years.
We actually have introduction to neural network, but it was very fast. Like I can remember it took more than 2 lectures actually.
Okay, we will do them together. Nice, we will do it. We will redo it from scratch. So I will assume that you guys are not familiar with convolutional neural networks, okay? So basically, the convolutional of an image F with a, what is it called? H as a kernel. Let's define it using images, right? I hate these images. Let me do it manually. Whee. So this is our image. This is our kernel. And this is our output image. For every single pixel, yes. So let's say we are taking this pixel here. It's mapped to this pixel here. What we do is we take this kernel, put it on this image, and we calculate a multiplication between the different points, right? So this point with this point, this point with this point, and this point with this point, right? We just do the multiplication between point-based, and then we do the summation. A very simple thing that I could do right now. Oh, I didn't expect that you guys don't know convolutional operations. So
we know actually, but it would be nice to refresh. At least you can see
yes.
what does
So
this formula
you're already
means.
familiar with logistic regression.
Of course.
Nice. So just honestly, it's just a complication of logistic regression. What's really happening in all of these neural networks is we are applying logistic regression to different parts of the image. So for example, if I want to calculate this pixel, what I will do is I will use logistic regression, or I will train a logistic regressor on these pixels, right? So what I will do is I will multiply each one of these pixels. This is the original image. I will multiply each one of them with a certain value, and then I will do the summation. Somebody can like remind me of the operation of logistic regression or of linear regression, right? So y, or output, equals a1 multiplied by x1 plus a2 multiplied by x2 plus so on and so forth, right? So this is what's happening for linear regression, and this is exactly what is happening for our convolutional neural networks. The only difference is now that we are moving this kernel along the image in a certain way, right? So basically, let's build one. So let's say this is our kernel. I hope I could move this. Yes, so it's moving like this. You see? So this is how it is moving. So this is the convolutional operation being applied to each one of them. Every time it highlights or it selects a group of 9 pixels, it does this multiplication and addition or linear regression, and it calculates the output. Of course, how do you find the weights of this linear regression? This is another question. As we said, either you find them manually or you use some optimization algorithm. But the algorithm itself is pretty basic, right? As you can see here, very simple, very basic. The operation of convolution is just an extension of linear regression. And of course, neural networks also in general are just an extension of logistic regression, right? I think if you guys are going to attend the elective course, I'm definitely going to give you like a long recap about these concepts of machine learning, where we will speak about like convolutional neural networks and neural networks in a more detailed way that kind of simplifies this idea for you. So for example, what we do is here we have our kernel, right? Here we have the highlighted part of the image. What we do is point-based multiplication, and then we do a summation. Very simple, right? So let's speak about how can we apply this for noise removal. So what is noise? Basically, noise is any unwanted contamination of an image. Why we have noise in image? So many reasons. Some of these reasons can be the imaging sensors were affected. Interference can be added to an image during the transmission. Sometimes, for example, in those things that kind of do transition between digital to, I don't know, something like that. For like old TVs, they used to do this transmissions between like satellites and stuff. So some of the bits of the image can be like changed during this transmission period. So it's you can get a lot of noise in your images, old photographs, so on and so forth. So yes, for example, going from analog to digital converter errors, right? So this is very common in that era. But nowadays we are like with like optic fibers, right, for transmission of the internet. So it's more reliable, and your bits usually do not get contaminated. So here we have, for example, a colored image. So as you can see, and here we have a noisy colored image. Here we have a grayscaled image, and here we have a noisy grayscaled image. Yeah, common type of noise. So there is this Gaussian noise. So principal sources of Gaussian noise in digital image arise during the acquisition, right? So when you're acquiring this image, the sensor has inherent noise due to the level of illumination and its own temperature. So in most cases of your, in most of your like photographs and all of these things, you are usually including a noise detector or like noise removal operation directly in the camera itself. Or for example, in some cases, the electronic circuits connected to the sensor inject their own share of electronic circuit noise, right? Noise models. So noise must be joined with the image data in some way, or throughout, either while we are acquiring the image or while we are transmitting the image. And the way in which we model this depends upon whether the noise is data dependent or data independent. Meaning there are two main branches of noise that we could deal with. Additive noise models, which are the easiest, which are data independent noise, right? So it's not because the image is an image of a horse that it had like a random bit changing. And there are the multiplicative noise models, which are data dependent noise models. A very simple model, which are the additive models, they're represented in this way. So basically your image, here it is or your noisy image, right, is represented as the perfect image, G, plus the noise, right? Very simple model. Now the multiplicative model, which is a bit more problematic. So here we have your actual image or your output image, the one that you are working with, is equal to the original or the ideal image, G, plus the original image multiplied by some noise, right? So here, this is the noise term, right? And the noise term is data dependent. So this is more problematic case, and usually it's a bit harder to fix than the additive models. Noise reduction techniques. So we have this linear spatial filters, and we have the non-linear spatial filters. Linear spatial filters, as your friend has suggested, for example, we have the averaging or smoothing filter, and we have the Gaussian filter. And the non-linear spatial filters are, for example, order statistics filter. We will see what order statistics is. It's very simple, right? Very basic stuff. So an average filter or smoothing filter, very simple filter that does exactly what it says, what its name suggests. And I think one of your friends already suggested this filter the second that I said that we are going to use this neighborhood smoothing filters, right? So these averaging filter, what it does, it takes the average of your neighborhood. So you define the size of the neighborhood. So for example, we have the neighborhood of size 7 by 7, we take the average of all of these pixels, and this will be the center pixel in the output. Okay, very simple, very basic algorithm. What this allows us to do is basically to reduce the noise and the level of detail simply by relying on the average of the area, right? So other terms used for it is box filter, and it replaces a pixel with its local average, right? So it has this smoothing and blurring effect. This is what we will see basically when you take, right? So let's say we are speaking about this edge, right? Yeah, I'm speaking about this edge. If I take the average in this place between the white pixels and these brown pixels, right? The edge will no longer be very obvious like this, right? So the edge will be very smooth or blurred out. So this is the effect that this smoothing or this, averaging algorithm does, right? So basically it takes the edges and it makes them less obvious or less clear. So this is the blurring effect that happens, and this is why it happens, right? Yeah, this is like a standard average. This is the weighted average. Depends, of course, on what you guys want. Both of them are very reliable. This one is more blurring. This one is less blurring because it focuses a lot on what is inside this pixel rather than what's around it, right? So for example, in this case, what should we put here in order to get a weighting average, right?
25.
25. So it's 5 multiplied by 5. Yeah, 25. Very well. Wow. Nice. So the smoothing filter, which is a linear filter, or the averaging filter, this is what it actually does. As we said, it goes through the image in a kernel way, right? Remember those kernels and convolutional? This is just another convolutional operation, which its weights are all the same, 1 divided by 9, or they could be different depending on what you guys want. But they are all the same for all the pixels and all the pictures. They just go through them and they give you the output, right? How to deal with the edges? There are a few approaches to deal with edge pixels. So Amit, what are edge pixels? I'm not speaking about what I was saying before, the edge of the box, or for example here. No, we are speaking about the edge of the image, right? So this is the edge of the image. Okay, let's go back. Now the edge pixels could be a little bit problematic, right? Because this pixel, right, it maps to the exact same place in the output, but we cannot, for example, put all of the kernel on it, right? So in this case, all of these pixels are empty and the calculations can be a little bit problematic. So we need to just define certain algorithm that fixes this problem. One is to omit the missing pixels or pad the images. So basically we add some black layers on top of the image, replicate the border pixels. So basically we repeat them, or we do this truncating or of the image, or any other way to do it. There is no like correct way to do this operation. All of them are valid. All of them give you a certain result, right? Yeah, there you go. So this is padding. A Gaussian filter is very similar. Now, now that we have finished with this simple linear filter of what is it called? Averaging smoothing filter. Now we will speak about the second filter, which is the Gaussian filter, right? So it's another noise suppression technique. Basically, what it does, instead of all of the pixels surrounding the image, surrounding the area of interest. So for example, here, This is the image. We are working on this pixel. Instead of all of this being the neighborhood and all of them being equally important to the output of our noise suppressor, now what we will do is we will build this Gaussian distribution around the image or around the point of interest. So this is how we define the center. The closer you are to the point, right? So in this place, right, we are, yeah, let's represent it in images or in colors. So let's say in this area, you have very strong weight. In this area, you have like, let's say 0.5 weight. And in this area, you are still contributing, but like with a smaller amount of, or with a smaller weight. So this is what the Gaussian filter does. Very simple filter defined using the Gaussian or a similar distribution to the Gaussian distribution. And it's a very simple one based on the X and Y, right? So the further you are from the point, the lesser influence you have on its output. So here it's the sigma or the standard deviation of our probability, depending on the standard deviation that you use. So for example, here with a standard deviation of just 1 pixel, only the pixels that are super close will be influencing. So you can see that it's a little bit blurred, but you can still see it overall. In this case, it's very, very blurred with just standard deviation of 5. We can see this blurring effect going even further when we increase the sigma, right? So the more you increase the more you increase the sigma, the lesser influence the pixel itself and its neighborhood has, and the more influence the further points have, right? And here we have the sigma to 30, and we can completely see that the object is kind of almost completely removed, right? So this is what the Gaussian filters do. And this is what noise removals do in general. So this blurring effect, right? So just so we could understand, so this is what blurring actually is taking out, right? So what we do is we take an image, we subtract its blurred image, right? So you know how to calculate this one simply by either sending through a averaging kernel or by sending through a Gaussian noise remove, or by sending through a Gaussian noise removal operator. If we do the subtraction between these two, we have this mask, right? So this is what comes up. So we are removing all of these edges, right? Now, if we would like to add it back, of course, with a certain parameter, this will add this sharpening to our image, right? So you can see that the edges now are much stronger. So for example, his wrinkles appear to be much stronger in the sharpened image, right? So this is the difference between blurring and sharpening. So these are how these two operations are being done. Now, the last part of window or neighborhood filters are the order statistics filters. And simply what they are just non-linear spatial filters. Remember the first filter that we used takes the mean. Another person would say, I don't want to take the mean, I want to take the median, right? So again, nobody can tell you not, nobody can tell you you are wrong. You could take the median filter, and sometimes the median filter gives much better results than the average filter, right? So for example, here is a, what is it called? Yeah, here is a thingy. Here's the image. These are the pixel values. Can somebody tell me what is the, what is the median of these values? Or how do you calculate the median of these values?
We ordered the
Yes.
sequence and
Yes.
choose the one that in center. And if there are two,
Oh, nice.
so if the sequence has even length, we can choose any of two, but maybe
No.
average of them.
Yes, we take the average of these two, right? Very well, nice, correct. So as your friend has said, exactly is correct. So basically we order all these pixels inside our neighborhood, and then we go to the ones in the middle. Of course, if you have, like, for example, this case 1, 2, 3, 4, 5, 6, 7, 8, 9. So if you have 9 values, then the one in the middle would be the fifth. In this case, you have 4 on this side and 4 on this side. If for some reason you had 10 or an even number, what you do is you go to the fifth and the sixth and you take their average. Okay, so this is how you calculate the median. It's a very simple operation. And if we compare it, so for example, this is some noise from glass effect. This is the removal using the median filter. I'll just clean up my screen. Yeah, nice. So here, for example, you see that we use this on a very, very noisy image, and the results are very impressive, right? So the median filter is quite nice. This is the noisy image. This is the filtering using average filter. This is the filtering using the median filter. You see that it's very clean. And this is why, no, not this is why. This is mainly because average operation is very influenced by outliers, right? So we already know that, and average is bad, median is good. These are just some geometric operations. So geometric filters are used to basically change kind of the perspective that you are looking into the picture. So for example, in this case, you see if you take an image too close to something that is rectangle, something that is like line, right? So this was supposed to be a straight line, but it's not a straight line anymore, mainly because you took it too close and the camera was a bit high. So the output of the image was kind of wrong, right? So the image that you are looking at in here kind of suggests that this is not a straight line, but kind of like a curvy line. And this is wrong. So we're trying to correct this using these geometric operations. So why do we need these geometric operations? So one would be to correct the effects of camera orientation. Another one would be to correct the images for lens distortion, align images that were taken with different sensors, or image morphing or other special effects. Usually all of these transformations, they don't really go too further, like too complicated. The one that we are going to speak about are the affine transformations, right? And they're defined using this simple multiplication, right? So this is just vector multiplication. It's not like pixel-wise multiplication as we did before. Now let's look at the influence of each one of these different values, right? There is the translation, what is it called? The translation affine transformation, which is the following, right? You put 1, 1, 0, 0, and a value here, a value here. This allows you to translate by m values along the horizontal axis and n values along the vertical axis. No need to do this, right? So basically, this is what, this is what it does to your model, right? This is one example that can shift or basically translate your image in a certain direction. Another one would be, what is it called? Scaling, right? Or zooming in, expanding and shrinking. So here we have a change of A in horizontal axis and a change of B in the vertical axis. We put A in this place and B in this case. So for example, if I wanted to combine both translation with scaling, what you do is you put A, B here, M and here, and then they are multiplied with each other, right? So basically they're scaled and expanded and or shrunk if the value is smaller than 1, of course. Checkpoint. Yeah, let A or B go negative, what will happen if these two get negative? Can you tell me?
It will be mirrored.
Someone else try? Right, so basically it goes this way if it's, yeah, it goes this way if it's positive, and it goes this way if it's negative, right? Do you agree with your friend or no? Just think of it, right? So let's say a pixel was here. Not in the center. Let's take something that is a bit far from the center. It was here. What would happen to it? It would go in the opposite direction, right? So as your friend has suggested, it would get mirrored, right? Either it's expanded like this, or it's like inversed, right? And of course, the length depends on the value of A and B, so the absolute value. Now, rotation is dependent on the angle theta. So if you'd like to rotate by an angle theta, what you should do is just basically multiply it with this. So this is your transformation. If you would like to do some skewing like this, so what you should do is skewing by an angle of theta, 1, 1, and tan of theta. I think, how much time do we have now? Yeah. So I think we don't have enough time to finish all of these and to basically do some derivation of these operations. But these operations are quite simple. So as you can see, it's just a basic multiplication, or what is it called? It's not, how do I call this? Yeah, so it's basically a affine transformation. Affine transformations are similar to what you have guys done in linear algebra. I'm sure you guys all have done some like basics of linear algebra and matrix multiplication. So this shouldn't really be too difficult, but hopefully we will get through this again in the next lecture. And I'm sure in the labs you guys will go through some well, interesting applications of these. You will see that all of these operations that we have seen in today's lecture, which are point operations such as background subtraction, contrast enhancement by finding the M, and depending on the E, we will have a different kind of contrast enhancement. I've seen these neighborhood operations such as these linear spatial features, either Gaussian or average. We have seen the nonlinear spatial features such as the median filter. We have seen these geometric operations such as affine transformations that could be used for different applications such as translation, scaling, rotation, and so on and so forth. All of these, they're very basic operations that can be implemented in a simple NumPy function. Do you guys have any questions so far? And I would like to ask you like a small proposition. Any questions? Nothing? Okay, nice. So, nice, here we go. So I wanted to ask your opinion about this. Usually in my courses, we always build like a mind map at the end of the lectures. Is this something that's useful for you guys? Like we build the mind map together very quickly. For example, let's say filtering lecture. What did we speak about in this filtering lecture? Go ahead.
There's the 3 types of filtering, like single pixel, like different, like 1 pixel, neighborhood, and statistical thing.
So we've seen pixel, neighborhood, and geometric, right? What else?
Why geometric? Statistical, no?
Not yet, not yet. So these statistical are inside the neighborhood operations, right? You see?
Okay.
Nice. Go ahead. Pixel operations, what have we seen? What do we use background subtraction for?
To detect if there were any objects.
Yes,
In
motion
motion.
detection, right? Very nice. Another pixel operation, which is? Go ahead. Open your mics and
Interesting.
Contrast enhancement. Neighborhood operations, we have seen
Averaging.
averaging.
And medium filter.
Okay, so let's call these linear. And nonlinear. So the linear, we had averaging, and we had the Gaussian filter. For nonlinear, we had the median. Can somebody tell me what are they used for?
To remove noise, for example.
Yep, noise removal or blurring. This is what they're used for. How do we make blurring into an algorithm of sharpening?
We subtract it and add the result to the original image or something.
Add it back. Very well. For geometric operations, what have we seen? What are they used for? So random affine, transformations. And what are they used for? Just a few examples.
Change of perspective.
Translation, changing the perspective, rotation, something else,
Shrinking.
shrinking, and well, zooming and shrinking. Let's call it shrinking. Very well. Thanks a lot. So this is it. This concludes our lecture for today. I will send you guys a screenshot of this beautiful mind map, and that's it. Thanks a lot for attending.
Before saying goodbye, could I ask you to put a grade distribution between all assignments and participation exam things in the Moodle? Because now we have old one for the previous year course.
Okay, thanks a lot for telling me that. I will do it, yes. You guys already have it in the lecture one, right?
I personally did not find this, but maybe I was not so careful in finding. But anyway, it will be nice if you put it like in the section that
Yeah, of course, no
is
problem.
aimed for this.
Yeah,
Thanks.
no problem, thank you. Anyone else has any questions?
And is it possible to upload presentations before the lecture so we can follow?
Yes, no problem. Yep, we can do that.
Thank you.
You're welcome. Thank you.
Thank you.
Have a good day.
Thank you. Goodbye.
Thank you. Goodbye.
Thank you.